Our next two speakers will be a very nice back-to-back. They're both people who've played a critical role in the Intergovernmental Panel on Climate Change and in the current assessment that has just been released this year. The first speaker is Dr. Bill Collins, and he's a professor in residence in the UC Berkeley Department of Earth and Planetary Science and head of the Climate Science Department at the Lawrence Berkeley National Lab. A leading climate modeling expert, his research is focused on the changes in the energy balance of the Earth system and the implications of these changes for the future of our climate. Prior to coming to Berkeley, Dr. Collins worked at the National Center for Atmospheric Research and the Scripps Institution of Oceanography. He's a lead author of IPCC Working Group 1, the Physical Sciences. He was also a member of our steering committee and has contributed widely to the dialogue on advancing interdisciplinary leadership on climate change on the Berkeley campus. Bill, thank you for being here.
David, thank you very much for that kind introduction, and I would also like to extend my thanks to the Philomathia Foundation for making these 2 days possible, and especially our public forum today. This is really a very timely topic for all of us to connect water, climate, and society. And my charge this morning is to deal primarily with the connection between water and climate, and then our next speaker will begin drawing the connections between water, climate, society, and the environment. But I will deal with the first pair of those topics. I also need to sort of move back from the focus that we've heard from our first speakers this morning, a focus at the city level and at the national level, for a couple of reasons. The first is that the IPCC is what it is. It's an intergovernmental panel on climate change, really commissioned by the UN to deal with the global problem. And so what I'm going to show you are global results. There's some regional specificity in the report, but I think it's also important for California as a very important part of the Pacific Rim to think about this problem in at least a pan-Pacific context. And of course, Berkeley is a global university. And so we draw students from around the entire globe. We also send those students back to influence their home countries. And I think it's important, therefore, for the university to think about this in a context that really spans local to regional to national to global. And so I'm going to show you primarily what the global implications of climate change are, as summarized by the Intergovernmental Panel Fifth Assessment Report. And I'm, like any good academic, I have incorporated, I'm sorry to say, acronyms in my title. So pardon me. And there will be points in this talk when I'm going to have to sort of translate from IPCC to English. Please bear with me. If you have questions about that, please don't hesitate to use the cards that will be coming around. I'll do my best, but there are times when that translation won't be perfect. So it's a real honor to talk to you about this report. And the next speaker, this is done as sort of more or less as a relay race. And it's always set up that the Working Group 1 gets to finish first, but the Working Group 2 and Working Group 3 will be completing their reports in spring of next year. Chris has been the co-chair of Working Group 2, and his report will be issued, I believe, in March of next year. So all these three reports will be released to the national and international community in very short order. And our report deals with basically the physics of climate change and its implications for our environment around us. And I wanted to start by showing you, just sort of illustrating this process a little bit. So there were in the picture in the upper right-hand corner shows you let's see if this laser pointer actually works. Actually, I'm not even going to use the laser pointer because I've had too much coffee this morning. My aim is not going to be particularly true. The picture in the upper right-hand corner shows you the 300 people who worked on Working Group 1 in Tasmania, and I'll come back to Tasmania in just a second. They made sure that we racked up lots of frequent flyer miles as part of this process, and we had a huge carbon footprint. And my chapter, of which I was honored to be a part, is in the picture of us is in the lower right-hand corner. The cover of the report is shown in the middle, and then some of the implications for California are shown in the left-hand figure. So this panel is commissioned by the UN to assess the state of knowledge of climate science. We do not do research. Our goal is to look at the literature, look at the state of the science, apply a strobe light to it, and come up with what we know in the year 2013. and to refer back to what we knew previously to show what progress we've made, and also to illustrate where there are still major gaps. Those are kind of our three major functions as part of this report. I mentioned Tasmania. We had a particularly hot and fiery setting for our last meeting. It was in Tasmania, which is just south of Australia. Australia that year had a record-breaking year. This is before the government switched to becoming extremely conservative, and so the new government is now denying the connection between the fires that are occurring right now and climate change. But at the time of our last report, they had a government that actually conceded the point and wrote a report called The Angry Summer of 2012 and 2013. The upper right-hand figure shows you fire danger across Australia, which peaked. They had to add a whole new set of colors to their temperature graphs to indicate how hot it was in Australia, colors they never had to use before. The picture in the lower right-hand corner is a cloud being formed by a fire over Tasmania. So they had pyrocumulus clouds forming during our meeting. And in fact, when we were flying home, it was 120 degrees Fahrenheit at the Sydney airport. There were fires on the tracks between the national, domestic and international terminals, which shut down the train system. And when we got on board the plane, the air conditioning system crashed 3 times because the air conditioning was trying to vent heat from a hot air conditioner into even a hotter atmosphere. And any of you know how refrigeration works know that that physics just won't go. So it was we were sort of living the report here in our last meeting, quite dramatic. This is also, when we were wrapping up this report, climate change was also coming a little bit closer to home. Last year was the hottest year on record in the United States. The picture in the upper right-hand corner shows you which states, the ones that are in deep orange, ones that are the states that had the hottest temperature ever recorded in national records by the National Climate Data Center. So it's pretty much the center part of the country had record temperatures, 120 years in the making last year, completely unprecedented. So we know that the climate is changing, and the other theme behind the symposium is both the challenges and opportunities. I'm going to sort of present, I guess, the challenge side of this, which I would like to essentially summarize for you as follows. We have built our society over the last 10,000 years in a period of extraordinarily stable climate, and that has been tremendously beneficial to figuring out where the best places are to grow crops, where the best places are to put cities, and we have cities that have been around for literally thousands of years, places like Rome, London, cities that have grown up and have established and developed rich cultures, and those cities and those localities are now going to be challenged by the fact that the climate around them, that climate envelope that we relied on to be so stable for 10,000 years, is changing. So I'm going to talk to you about the challenges that this poses from the standpoint of water, because that's the theme of our meeting this morning. So our climate is changing, and this picture sort of illustrates the various ways in which it's changing. And all of these, I should say, every single one of the arrows on this graph correspond to real data. So this figure is backstopped by an enormous amount of observations being collected from the ground, from the air, from ships, from space. So these arrows are not speculative. There are numerous data sources that essentially determine the sign and the magnitude of each one of these arrows. And the ones that I want to point out to you that are relevant to water, in particular, are that glacial volume is decreasing. There are a number of places around the world where glaciers and melt-off from glaciers form a primary source of water. Boulder, where I came from, gets 1/3 of its water from the Arapaho Glacier. That glacier will not be there by the end of the century. This is also true of the Himalayas. The Himalayas, glaciers are melting at a fairly rapid rate. That's going to potentially pose a supply for water much later, but will pose a water supply problem. Snow cover is decreasing. There are any number of changes that have been observed, and we know this is happening. So the question is, what does this mean for our water supplies? And one of the key things in order to understand the issue, the connection between climate change and water, is to understand how temperature and water are linked. We also know quite reliably that the planetary temperature is increasing. This shows you one of 4 different data sets that all agree. This one is from the Goddard Institute for Space Studies. That's what GISS stands for. And it shows you the change in the Earth's surface temperature over roughly the last 100 years. And everywhere where there's a plus, means that the trend is highly statistically significant. And the warm colors in this picture indicate where it's increasing. And in case any of you need a sort of a handy back-of-the-envelope guide converting between metric, and everything I'm going to show you, I'm sorry to say, is in metric. This is an international report, after all. And most of the world has sort of moved on beyond English units. So in case any of you need a handy guide here, just multiply by 2 in order to get degrees Fahrenheit, roughly, in order to convert. So virtually all the planet has been heating, and some places more than others, but you can see it, particularly at high latitudes, places like Alaska, Canada, and Russia. And of course, you can't actually see Russia from Alaska, but in any case, they're all they have heated by on the order of about 2 to 2.5 degrees centigrade, so on the order of about 4 to 5 degrees Fahrenheit. It's getting much warmer at high latitude. As the system gets warmer, its capacity to hold moisture increases. So the amount of moisture that the air can hold increases exponentially with increasing temperature, and the atmosphere is warming along with the surface. This is something that's been known for some time. And so because of this connection between temperature and water, there's a connection between the increased warming and the hydrological cycle on which we depend. And this is our cartoon of the Earth's current hydrological cycle, the way that someone like me would look at it, which is globally, typically. And this shows you the colors indicate the amount of rainfall every year in centimeters per year. Remember, for those of you who are kind of doing this in your head, 300 centimeters is roughly equal to, let's see if I can, it's roughly a yard. So is that correct? No, it's a foot. It's a foot. 1 meter equals, yeah, boy, 1,000 centimeters equals a yard. So just in case you're keeping track, 300 centimeters equals a foot of rainfall. So purple equals a foot of rainfall. And what we see in this graph are bright orange colors indicating where there's a lot of rainfall, the major storm tracks, high precipitation along the equator. This is the pattern around which we have built, for example, we have a Mediterranean climate in California because we don't get, Seattle gets all the rain, or a lot of it, and we get less rain in California. We do get some from the Pineapple Express. This is the pattern that we're now seeing change dramatically around us. So the changes, so here's the pattern as it's existed now for millennia. Here's what's happening to it. So again, the arrows are showing you how this global pattern of movement of water is changing. The basic things I want to call out to you here are that the storm tracks in both the northern and southern hemisphere are moving toward the poles. And there are places which are dry that are going to get drier. And this sort of theme of the wet getting wetter, the dry getting drier, is going to come back over and over and over again. Climate change seems to be sort of amplifying and hardening this pattern that we have in the present day climate. And here it is manifested in a way that's kind of slightly more obscure, but the upper picture is the one that's relevant. That's the trend in the amount of water in the atmosphere. Where it's blue, we're getting more water. Where it's orange, we're getting less. And you can see that where it was already kind of dry in these zones where the atmosphere is sinking in the Pacific Ocean, that it's getting even drier. And where it's moist, for example, right along the equator where there's a lot of water vapor, it's getting even moister. So these patterns are getting bigger with time. And that's having an impact on ocean salinity. That's the other implication of this particular figure. Now, this is one of those figures I would be remiss if I didn't show you the technical background. So some of these figures were designed for the technical summary or the summary for policymakers, and some of them were really the kind of the raw data. And I'm going to sort of skip between the stuff that's a little bit more slated toward ministries of environment and then people like, technically cognizant people. And this is one of the graphs that's slated for technically cognizant people, so my apologies. And you can see that the annotation in the lower right-hand corner is the figure number from the report. Let me translate this graph into English. What it's saying is that in 100 years, the storm tracks will move by about 1,000 kilometers northward, which is about, almost the length of California. That's what's happening. And that will move water, way up the coast of California into Canada. That's what's, and we know this is happening. There's data on here, there are models in here, but the data is pretty unambiguous. That means that there's going to be a dry zone left on the southward side of the storm track. That also has big implications for water supplies. Okay, so how do we translate this information into projections? So climate models predict the Earth's future. And I'm one of the many people who've contributed to climate models around the world. There were 45 different climate models that contributed to the projections, and I'm now going to switch into the part of the talk that deals with the future. These models are quite capable. So this is water vapor from a model that I've been helping to construct at 25 kilometer resolution. So this is about the distance between, if I recall correctly, between Davis and Sacramento. And this model is now able to track hurricanes, and it actually gets quite reliable hurricane statistics if we were to compare against present-day climatology. In the interest of time, I'm not going to let this movie run, but the idea is that we have models that can really emulate nature, and we can test that assertion against observations of the present-day climate. We've also benefited from our proximity to the motherships. I was particularly pleased that Lisa Jackson has joined Apple, because we've benefited tremendously in California from being close to the heart of computing innovation really around the globe. And what's happened is that as the computing has sped up by a factor of 1 million over the last roughly 10 to 15 years, our models have been able to zoom in to greater and greater regional specificity. And this gets back to the point that we heard from the mayor earlier. Now, 110 kilometers is getting down to about the size of the greater LA basin. That's still not going to cut it as far as the projections that we need. If we want to look at the connection between local to global, we need to go to a model that can do the globe and do local all in the same system. And that model is coming soon. So we think that by the end of this decade, the beginning of the next, we will have computers that are capable of resolving the gradients of climate change down into the Bay of San Francisco, which is really quite a remarkable development, and will be an important one for us to extend the capability that LA has pioneered across the state of California, across the American West, and in fact across the country. And so we look forward to being part of this pioneering exercise to kind of push the envelope and to be able to connect local to global climate change. That's going to be very important for all of us. Okay, so now I'm going to switch into the part of the talk that deals with the future. And again, I'm going to show you a few graphs that are a little moderately technical. So what is this graph telling us? On the left-hand side, it shows you scenarios for carbon dioxide. And it's expressed in terms of parts per million, which is probably an unfamiliar unit. We are currently at 400 parts per million of CO2. We started back when the steam engine was introduced at 270. Okay, so we've increased, and when I say we're quite confident that it's have increased CO2, more or less increased it by 50% over this time period, from 270 to 400. The scenarios here range from 360, which is sort of what some people are advocating for us to return to, all the way up to nearly 2,000 parts per million of CO2. Just to put in context what 750 parts per million, which is sort of the intermediate scenario, means, 750 parts per million equals a level of CO2 that the planet has not experienced for 34 million years. 750 was what we had when the Antarctic ice sheet began to form 34 million years ago. So we've managed in 300 years to reproduce 30 million years of changes in carbon dioxide. We've basically punched the accelerator in kind of the worst possible way to go back in time. And this is, I think, as become evident, perhaps not the brightest thing we've decided to do. So the other thing that this graph makes clear is if you look on the right-hand side, that the CO2 concentrations map directly onto increased temperatures. The higher the CO2 level, the higher the temperature change. And this, again, is expressed in degrees Celsius. You might think, oh, geez, 4 degrees Celsius. I mean, if I went to graduate school in Chicago, and believe me, that's the difference between morning and afternoon, and not such a big deal. And does make a big deal when you start applying this stress very rapidly to ecosystems, as we'll hear about from our next speaker. And when you look at how this pattern lays itself out over the globe, this relatively bland-looking change is actually a very big game changer. So the warming, as I indicated earlier, alters moisture and rainfall. So the warmer the atmosphere, we get enhanced moisture, weaker circulation, more rain. And I'm going to show you now, this cartoon is translated, I'm sorry to say, in a couple of graphs that follow that are moderately technical. But this correlation between higher temperature and higher moisture is backstopped by observations and by models, and that's what I'm going to show you next. The connection between higher temperatures and higher rainfall is what I'm going to show you in 2 slides. So brace yourself, but here's more of these kind of wonkish figures. So this lays out, the only thing you should take away from this figure is the correlation between temperature on the horizontal axis and moisture on the vertical. And you'll notice that it's a dead straight line. The observations are on the lower left-hand end of this graph because that's where we are currently. If you allow the climate to warm, you march straight up that line to a much moister climate. That moisture, however, is going to be unevenly distributed, as you'll see in a second. A lot of it's going to reside over the ocean. The land atmosphere will actually get, the relative humidity is probably going to drop over land around most of the globe for a variety of reasons. Correlation between temperature and rainfall, right here. Look at the lower graph. The higher the temperature on the horizontal axis, the more rainfall on the vertical axis. Again, the models support this assertion of connection beautifully. And it's backstopped again by observations from the present day. Okay, so what does this mean for the hydrological cycle? So this is and the hydrological cycle is the jargon that climate scientists like myself use to refer to the motion of water through the climate system. So this is the transfer of water by evaporation from ocean and land into the atmosphere, its circulation, its formation of clouds, the formation of rainfall, and the return of that water from the atmosphere back to the land into the ocean. It's a cycle that's being driven by the input of solar energy that drives the evaporation. And so we refer to a hydrological cycle as referring to all of these processes connected together as one seamless system. Let's look at the precipitation graph on the top. This is the change in precipitation that we anticipate by the end of the 21st century following one of the more aggressive emissions scenarios. And again, the colors are here to sort of guide your eye. Brown colors indicate where it's going to get drier. Blue indicates where it's going to get wetter. And what you'll notice is that there's going to be a dramatic increase in rainfall over, for example, portions of the tropical Pacific where it's already quite moist. There are also places where it will get appreciably drier. And so let me call your attention, for example, to the entire Gulf of Mexico, to Brazil, which has one of the most important rainforests on the planet that serves as a major sink for carbon dioxide. This drying is going to amplify an existing tendency for the eastern part of Brazil to already be quite hot and dry, and that pattern will be amplified by climate change. It's hard to tell, but the southwestern United States is also getting drier under this scenario, and there are portions of Africa that will also get appreciably drier, adding to existing stress, for example, that's already been plaguing the Sahel and elsewhere, as we'll hear about later on in this symposium. These changes in rainfall, and they're expressed in millimeters per day, and just so you have a handy guide to do the translation, there are roughly 3 millimeters per day of rainfall that fall around the planet. So this is actually a pretty big, some of these changes are quite large relative to that normal amount of rainfall that falls. This is a major and what appears to be nearly permanent shift in the climate. The other thing that's unique about climate change relative to something like an air quality issue, where a simple rain event will clear out the smog. Of course, it comes back again because people get in their cars, but the rain will clear the smog out. These greenhouse gases that are driving this change have lifetimes of, in some cases, centuries in the Earth's atmosphere. So this is not a problem that where even if we were to stop emitting tomorrow, we've already set the climate on a course of change. And that change will continue even if we were to dramatically ramp back our emissions. However, the sooner we ramp back, we can avoid a scenario that looks like this. This is a pretty serious scenario in terms of changes to the water cycle. Relative humidity, as I indicated earlier, the ocean regions get a lot moisture, dramatic drops in relative humidity over land surfaces. Snow will decrease as well. This is showing you the percentage change. And I want to come back to this in a moment in connection with California, because this is a big deal for California. But global snow extent under the motion, and so the lines in the upper graph go from the blue is the least dramatic emission scenario, the red is the most dramatic emission scenario. Under red emission scenarios, we lose 25% of the snow cover on the planet, putting greater stress on plants and certainly a greater stress on places like California that rely on time-release water from snowpack. Frequency of extremes will increase, and this was also going to pose a challenge for us because you may remember what happened when we had the Pineapple Express last December, flooding, landslides, etc. Those are slated to increase for California by the frequency will increase by a factor of 3 by the end of the century, those kind of extreme Pineapple Express events. So we're seeing, and the mayor mentioned the heat waves that are going to begin occurring across the LA basin and also in the eastern part of California. Again, these arrows correspond to patterns that are already manifest in the data. In some cases with less confidence than others, but climate change is going to sort of amplify these changes that we're already measuring, already seeing in the climate record. And I will just show you, I've been sort of hitting on this theme for a while, but the wet gets wetter, dry gets drier sort of amplifies, so more extremes. And the frequency between these extremes is also going to change dramatically. This is, again, one of these, this is supposed to be a sort of a public-friendly figure, but I don't think it is in my book. It's got like at least 3 different acronyms in the title. But the point of this figure is that extreme rainfall events that would normally would have been spaced 20 years apart, that spacing will shrink or collapse under climate change. So, for example, everywhere where it's deep blue, events that used to take 20 years will now take 2 years. They'll come back every 2 years. So if something causes a flood every 20 years, hey, it's back every second year. And remember what happened to New Hampshire. They lost bridges that had been in place for 200 to 300 years when they had that really strong rainfall event a couple of years ago. That's going to become the norm under extreme climate change. What this means for California is to get back to the issue of water supplies and bring this a little bit back closer to home, is a loss of the snowpack that we relied on as our time release mechanism for water. And so let me explain to you what this graph shows. There are sort of 4 panels. The left 2 panels show you the change between sort of from now up to the mid-century. And then within that time period, there are 2 panels again, one showing you the effect of lower and higher emissions. Higher emissions, in this case, higher emissions is actually lowballing what we're currently doing. So this was done, this figure was prepared for California by the California Energy Commission, and some of the authors of this report are in the room today. This was based on some older emission scenarios. The current emissions patterns actually exceed the high emissions figures that are shown on here. But we'll be down by 60% under business as usual by the year 2050, and down to 10% of our snowpack roughly by the end of the century. And that has big implications for what we do with our water infrastructure, which we need to begin dealing with. And again, it's potentially a solvable problem because California may actually get more total precipitation in a warmer, moister climate. It's just going to be falling as rain, not as snow. We're very confident in this result. We're not sure how much rain is going to be falling, but we're sure it's not going to be falling as snow. Okay. So with that, I would like to sort of conclude with some statements that are from the technical summary. This is sort of a distillation of the IPCC Working Group 1 report. And by the way, you can find this report very easily by just Googling IPCC Air 5. And all the details I've shown you are online now in electronic form. But I wanted to connect, the challenges for future water resources, and we're going to hear a lot more about that from Chris in just a moment, backstopped by the data and the evidence coming out of what we can already see in the climate system. And this is, so we have built our world around water that's very inexpensive. It's almost certainly underpriced. It appears all around us in our natural environment, which is one of the reasons why we enjoy California so much, in our water supplies that we use for agriculture, for drinking, in the natural beauty of some places like Monterey Bay. All of these resources rely on water. And what we're certain of now, as evidenced in the IPCC report, is that that world of water in which we're embedded is going to change. And so it's that challenge that faces us now that which we must address. And I think we're now going to hear from the next speaker about the potential impacts of these changes. And then this symposium is really dedicated to the idea of, great, so we face a problem. Getting back to what we heard from Lisa Jackson, we have a challenge. What do we do about it? And so I am confident that we can address this challenge. but we sure as heck need to face up to the fact that it exists. So with that, let me conclude, and thank you very much for your attention.